This video is just some notes on properties of logarithms. So chapter 7, logarithms and triangles. Properties of logarithms, which was on your worksheet from today, but I'm going to talk about them here. And then solving exponential equations with logs, which was also on the worksheet. So properties of logarithms. So I'm going to go through 3 properties, and I'm going to go through some examples showing you how they're related on the calculator. So the first one is our product property here for logs. So if you have log, let's say base b of m times n, where you're taking log of a product, you can rewrite this as log base b of m plus log base b of n. So an example, let's say I have log base, I'm just going to do log, common log. So if I don't write a base, that means it's base 10, and that's considered a common log. So let's say I have log of 24. Okay, log of 24. So this is really log of, well, 2 times 12, which means I could really rewrite this as log of 2 plus log of 12. I could also have written this as log of, let's say, 3 times 8. So I could have done log of 3 plus log of 8, and that would give me the same answer as log of 24. Or let's say I did log of 4 times 6. So that would be log of 4 plus log of 6. So I'm going to put in my calculator log of 24, which again is base 10. If I don't have a base there, it's called the common logarithm. So that button is this one right here, log. You'll notice it's got 10 to the x on top. So I'm going to be pressing that log button. So if I do log of 24, you see I get 1.38 about. And let me show you that if I did any of these, log of 2, close your parenthesis, plus log of 12, I got the same thing. Log of 3 plus log of 8, I got the same thing. Oops, hold on, sorry. Watch my parentheses here. So log of 3 plus log of 8, okay. You see I get the same thing. Log of 4 plus log of 6. All of those gave me the same thing. So when I am taking log of a product, I can break it down to log of one of the factors plus log of the other factor. Okay, so that is one property. Next property is going to be the quotient, where I'm doing division. Okay, so let me break this down. Okay, so for this one, let's say I have log base b of m divided by n. And that's going to be log base b of m minus log base b of n. Now, really what's happening here is this log base b of m over n, this is really log base b of m times n to the negative 1. That's really what this is. And what ends up happening is I can then take log base b of m plus log base b of n minus 1 of n to the negative 1. Now, what we're going to learn in the next property is if you have log of something to a power, the power gets moved in front. So this becomes log base b of m. And then this negative 1, the exponent's going to move in front. And so I end up with plus a negative or just minus log base b of n. And that's where that comes from. Okay. So let's say that I do an example. Let's say I have log of 3. Okay. Now I can think of log of 3 as maybe log of 12 over 4. So that would be equal to log of 12 minus log of 4. Maybe I'm thinking of this as log of, let's say, 21 over 7. And that would be log of 21 minus log of 7. Okay, and that's a 21 right there. And I can do a whole bunch of other quotients that would be the same thing. And again, let me just kind of show you. So if I'm going to do log of 3, that's log of 3. And now let me do log of 12 minus log of 4. Log of 12 minus log of 4. I got the same thing. Log of 21 minus log of 7. I got the same thing. So any of these where these two numbers would divide and get me 3, I'm going to take log of the one minus log of the other. Okay. And the last one of these properties that I'm going to talk about is the one I kind of alluded to right here, where I'm talking about if I have a log of something to a power, the power gets moved in front. So let me look at that one. So if I have log base b of, let's say, m to the r, where r is my exponent that I'm raising m by, this r is going to move in front and it's going to multiply with log base b of m. Now, kind of as an example, how does this happen? So let's say I've got log of 2 to the 4th. Okay. Now, really, this is log of 2 times 2 times 2 times 2. That's really what 2 to the 4th is. So if I'm thinking about my product, where I can separate this and write each of the factors as a separate log with a plus, what happens here is this is going to become log of 2 plus log of 2 plus log of 2 plus log of 2. Okay. And so I've got 1, 2, 3, 4 of these. So this becomes 4 log of 2. So what happens again is when you have this, where you're taking log of something to a power, the power is going to move in front and multiply. Okay. And again, if I take log of 2 raised to the 4th, which is really log of 16, okay, and I take 4 times log of 2, you see I get the same thing. Now, this particular property is the one that's going to help us solve exponential equations using logarithms. So let me run through an example like that. So let's say we have 5 to the x is equal to 93, something like this. 5 to some power gets us 93. Now, the way we were solving these up to this point was I was trying to get both sides to be the same base, but 5 and 93 will not be the same base. So what I'm going to do is to get rid of this x being in the exponent, or to undo an exponential, you're going to log both sides. And to log both sides, you're just going to write the word log in front of them. So I'm going to take log of 5 to the x equals log of 93. Now, this right here, this exponent, when I'm taking log of something, and let me just say this real quick. I'm taking log base 10, your common log. That way I can put it in my calculator, okay? So I'm taking log base 10 of 5 to the x, log base 10 of 93, okay? And that's, again, what this is when there's no base there. Now, this exponent, when I take log of something to a power, the power moves in front. So I get x log 5 equals log 93. I'm going to divide both sides by log of 5. So I'm going to take log of 93 divided by log of 5. And I'm going to be putting that in my calculator. So again, this button here is my log base 10, my common log button. So I am going to do log of 93. Here, let me move this over. Log of 93 divided by log of 5. So I can do log of 93, close your parenthesis though, divided by log of 5. And I end up getting 2.8, let's say 2, if I want to give two numbers after the decimal, because the 6 will push this 1 up. So this is going to be 2.82. That is my answer. Now, if I wanted to double check myself and I want to see, does 5 to this power get me 93? Take 5, raise it 2. And on this negative button is the word answer. So to get that, I can do blue second button, and negative. And that's going to type in my last answer. And you see I get 93. Now, if I had come up here and kind of snagged this answer, and I would have done 5 raised 2 and come up here and gotten this, I'm not going to get exactly that answer because this is probably a rounded answer, not the exact answer. And you see I'm slightly off. It would round up to 93. But again, if I come here and use answer from down here, it will actually compute the whole answer without it being rounded. So let me do one more of these problems. So let's say we have a situation where I have one of the ones, kind of like the geometric ones we did in integrated 1, where maybe we have 2 times 7 to the power x is equal to, let's say 200. Okay, let's say something like this. So 2 times 7 to the x equals 200. Now, before you do anything, you want to get 7 to the x by itself. So I'm going to divide this side by 2, and I'm going to divide this side by 2. So let me just write this again. So I'm dividing this by 2, I'm dividing this by 2. And when I do, I get 7 to the x is equal to 100. Now, I am, again, 7 and 100 cannot be the same base, not a nice base at least. So I'm going to log both sides. So I'm going to take log of this side. And again, it's log of 7 to the x is equal to log of 100. But what I do is when I take log of 7 to the x, I automatically write this line I'm going to write right now. I know that if I take log of this, the x is going to come in front. And so I usually would just jump to x log 7 equals log 100. I'm going to then divide both sides by log 7. And I'm going to get x equal, and I'm going to put it in my calculator. Okay. Now, when I'm putting this in my calculator, let me just make sure we get the whole problem in here. Again, if I'm typing it in log divided by log, I can take log of 100, but I need to make sure I close that parenthesis, divided by log of 7. I can close the last one or not, it doesn't really matter because nothing else is coming after it. And I get 2.37 if I round up. Now you can also do alpha y equal, and that's fraction, okay? And then I can do log of 93, and I can close or not close, because if I'm not doing any other math on top of this fraction, I can close it, but I don't need to because it knows to close it, okay? It knows that I'm done. I want to calculate just the top. Now I'm going to calculate just the bottom. And that's going to be log of, 7. And again, I can close or not close, but up here I have to close this 100. And you see I get the, oh, sorry, I did 93 here. That should have been a 100. 100. And you see I get the same answer, 2.37, 2.37. So 2.37. Now you only use the logarithms when your x is in the exponent. If your x is not in the exponent, you're going to root it. So if you're raising it to the 4th power, for example, you 4th root it. If you're raising it to a fractional power, you're going to raise it to the reciprocal. So I will be adding on to some notes for this tomorrow. Again, if you want to copy these down for yourself, I will scan them also. But I'm making the video so you guys can hear me talk and not just see the work.